All right. So I saw the quiz last night. That silences people quick. So it's not that bad. I deleted essentially all the stuff that we don't know. I'm meeting with Ashvin after the lecture and after office hours, just to confirm a few things. But like, for example, here's some stuff I already, so I'll post the list of stuff we don't have to know on Piazza, and really the quiz isn't that bad. Like, you don't need to understand how to use exec and join because they don't know how to do it. You don't need to know about zombie and orphan processes because they don't know what those are. You don't need to know the goals of init because they don't know what that is. You don't need to know joinable or detached threads. You don't need to know anything about that @exit thing. You don't need to know anything about the MMU because we'll get to that later when we actually talk about virtual memory. You don't need to know x86 assembly or like any details that you have to do in lab 2. You don't need to know any C calling conventions. Again, anything related to lab 2. You don't need to know that, hopefully you don't need to know that set context, get context, because that's related to lab 2. So yeah. Sorry? So you need to know basically, so you basically need to know, you should really know what a system call is. You should know, the types of what jobs that the kernel or operating system are responsible for. And pretty much throughout all the quiz, whenever you see operating system, it essentially means kernel because the kernel is definitely part of the operating system. And all the questions are pretty much about kernel stuff. So like system call interfaces, you should know a bit about processes, what they represent, what they do, how you can kind of use them. You don't need to know any coding details about them. So you don't need to like fork bomb something. I won't ask how many processes get created for a piece of code or something like that. What we'll be doing at the beginning of this, talking about threading. So you'll need to know like cooperative scheduling and preemptive scheduling. So that's just like conceptually what we kind of talked about last lecture. So we'll talk about that again today. In today's lecture, you don't have to know about the locks, but any of the threading examples, like how threads work and how they might execute and what problems you may encounter, would be things that are completely valid. And yeah, anything from like the introduction, like what operating system does, you should know, address spaces and all of that fun stuff that we saw examples of. Yeah.
You said cooperative threads and the other one was, what's the term for it again?
Preemptive. So we'll see that again. So I'll say preemptive today. All right. So I guess I'll try and power through today's lecture and pretty much just concentrate on stuff that's definitely on the quiz, and then we'll leave the rest of it for later.
So is locks on the quiz or no?
No. So the locks won't be on the quiz, but locks are how you actually like synchronize between threads. So what threads do is definitely on the quiz. So let's go ahead and start that. And yeah, I'll post a whole list on Piazza after I meet with Ashvin. So what we saw last lecture when threads were battling over that global memory location is called a data race. And there is one definition for it that I guess you don't need to know for the quiz, but for quiz 2 and throughout all your programming with threads, you'll have to be able to identify data races and also prevent them because they're a source of all the nasty bugs that we see. So a data race is when two concurrent actions access the same variable and at least one of them is a write. And in that case, you can have inconsistent data and results that you do not expect. So when we talk about what data races happen, we have to know what atomic operations are, and atomic operations we touched on last lecture, but just to be clear, they're like indivisible operations. So that operation either completes completely, like the instruction executes, or it doesn't. There's no in between. You won't see, if it's a write to memory, you won't see like a partial memory write or anything weird like that. It'll either be written to or it won't be. So it either happens or it doesn't. And that means you can't preempt it. And remember what we were talking about with processes, and whenever they're context switched in and out, the kernel maintains control. Preemption is just taking away the CPU from something. You're basically saying, hey, I can take holy crap. I can take away the CPU from you at any given point, and then maybe context switch over to a new thread or a new process. Yep.
It's not about you said two concurrent actions.
Yep.
What if the two actions are in parallel?
Yeah, so the question is, on the last slide, it just says concurrent here. What about if they're in parallel? So if they're also in parallel, if you think of like a global state, they also happen concurrently because one will happen right before the other one because it's only to one physical memory location, for example, so they'll happen in some order, even if it looks like they happen at the same time. Yep.
For indivisible, for atomic operations, is that kind of like a move command, like in assembly? Like it's just one?
Yeah, so like a move command would just be atomic. It's either whatever you moved is going to be moved into that register or it hasn't happened yet. There's no in between where like only half of that register will get loaded or something like that.
Whereas like multiplication, if you didn't have an actual hardware thing where you just have to repeatedly add, that would not be atomic because it has multiple adds within it, right?
Yeah, so you can think of pretty much any assembly instruction you see will be atomic. So it'll happen all in one go. It'll either happen or not. So if you have to implement multiply yourself that has multiple assembly instructions, then, you know, if that was executing in a thread, you could take CPU away from the thread after any one of those instructions and start executing another thread, and you might be in some weird state. Yep.
So does preemption just mean like interruptible when it comes to concurrency?
Yeah, so preemption just means that you don't control when the CPU is taken away from you and when you get context switched out. Because remember, the only other scheme we saw yesterday, which is what you're doing for Lab 2, is cooperative threads, where threads have to give up willingly the CPU. So there's pretty much two strategies, and we saw them when we talked about processes too. Either you can willingly give up your CPU, which is cooperative, and problems with that, of course, is that if any thread or process doesn't give up the CPU, it can just run however long it wants. It can just not yield the CPU at all. And then the other option is preemptive, where essentially the operating system, or in the case of Lab 3, your threading library maintains control and takes the CPU away. So you don't get to control, essentially the thread doesn't get to control when it yields. Yep.
In assembly is like a preemptive, like when you preempt something, is that like you're running one command and then somewhere in the hardware it just automatically changes the program counter or something? Like, is that kind of what a preemptive is?
Yeah, so the question is what actually is a preemption? So when we talked about being able to context switch between processes and kind of how Linux works with true multitasking where it's preemptive, the kernel is going to set some timer interrupt and essentially interrupt itself to regain control of the CPU. It can do it with any other type of interrupt too, but essentially it has some access to special CPU instructions that the user process does not have access to, and it can kind of interrupt itself and then get control of the CPU back that way. Okay, so this is kind of an aside, just kind of getting into compilers. So there's a thing called 3-address code in compilers that just makes code easier to analyze and read instead of just using assembly. So it's mostly used for like analysis and optimization by compilers, which you might see if you take a compiler class, and compilers are really, really great. So this is kind of a preview for that, but the statements essentially just represent one fundamental operation, and for the purposes of this course, you can assume that each are atomic. So generally they'll map to instructions, but who the heck wants to read assembly? So you do this because it's useful to reason about data races. It actually kind of tells you what's going on in the hardware without actually having to read assembly. So the statements are all going to have this form. They're going to just have some result equal to, at most, an operand with an operator and another operand. And that's as complicated as they get. So they're dead simple, and you can represent the entire program just using statements that are that small. So GIMPL is the 3 address code used by GCC. If you dig into it, you can actually use these flags if you're interested. Again, this isn't part of the course, it's mostly for interest's sake. But it's generally a lot easier to read than just handwritten assembly. So if we look at that data race example that we saw yesterday, if you see the ++ count, and remember I was kind of alluding to that it's 3 operations, if you run it through GIMPL and see what ++ count actually is represented by, it's represented by something like that. So D.1 is just some temporary storage. The way it represents that kind of abstract machine is that it just assumes it has infinite registers. So the D dot some number is just a register, and it assumes that there's an infinite number. So the first operation that it would do is loading from memory. So it would dereference that count from whatever, because remember that's just a global variable, so it would have to read it from memory, and then it stores it in a virtual register, and then the next operation is the actual increment, which would happen locally just on that thread. So it's, a new temporary register equals D1 plus 1, so that's our increment operation. And then the final operation is just to write out the result. So D2 is the result of incrementing whatever we loaded, and then this is our write operation. Yep.
So if we have infinite registers, isn't that like abstracting away the whole like stack, where you're like pushing and pulling from the stack to get your variables?
Yeah.
And so wouldn't that not be like an atomic operation then? Because like in theory, if you're trying to get a value from like register 200, there isn't 200 registers. There's actually quite a few commands getting that value from the stack, no?
Yeah, but you don't really care. Because the stack is local to your thread, right? So you don't care.
But it could still be like interrupted, no? And would that cause problems? Like if it's preempted?
Yeah, it can be interrupted, but it would be interrupted while it's, extracting some value from the stack. And it's just going to resume and be fine, right? Because it's independent. Yeah, so this abstracts away all the kind of messy details. Okay, so let's go ahead and see, oops, I probably shouldn't show that. So these are our instructions. They're at the front. And then initially, if the address of that is 0, and we have 2 threads running, if we assume that we have, preemptive scheduling where we don't know which thread will run at a time and they can be interrupted at any single time, well, then at the first point, so there's 2 threads running those 3 instructions. Within a thread, they have to run sequentially, but between 2 threads, you have no idea what's going to happen. So what can happen is it's now a race. You don't know which thread is going to run first. So initially, we can say, hey, thread 1 is going to run, and it would run this read instruction. So if it runs that read instruction, it would read, if we dereference whatever p count is now, it's 0. So that thread would read the value 0, right? And then at this point, either it could continue on to the next instruction, or it could get preempted and then the other thread runs. So if the other thread happens to run right after that load, it would also, remember that its D1 is local to itself, it would also read the value 0. And now at this point, it doesn't really matter who runs first, right? Thread 1 could run again, and it would just increment whatever value that it read from D1. So D1 plus 1 would equal just to 1. And then because, let's just say it executes the write command, then it would write out pcount equal to 1 so now that memory location is equal to 1. Now it would switch back to the other thread so it can finish. So in that case, we'd get D2 equals to D1 plus 1, which would be again 1. So this thread would again write out the value of p count equals to 1. Right? Any questions about that? Because this is preemptive, so at any point, it could be taken away. We could also have thread 2 execute first, and then thread 1 could have executed, and we would have got the same result if they just did both their writes. And again, we could have had it slightly different. So this could have run second, and it could have executed like that. But that wouldn't have changed our results either, right? But if thread 1 ran to completion, so say we did all of these, oops. So if we did all of these and we actually executed thread 1 all the way to completion, then when we read the value of p count here, we would have written it before, so it would now be equal to 1. And now when we execute this, the next instruction where we increment the count, it would actually increment it to what we expect, so it would be 2. And in this case, it would write out 2, right? Which is hopefully what we expect. So there's a bunch of different orderings. The only things we care about if we argue about data races is accesses to the same location. So what we really care about is the read and the write. So if we argue about all the different combinations of things that could happen, there's not that many. So thread 1 could read first, and then at that point, only 2 things can happen. So either it would write immediately, or that it would get preempted and it would execute the next thread, right? And then if write 2 happened, then it would be write 1 it would be write 1 or write 2. So you can kind of go through that and see all the different combinations of interleavings between the 2 threads we would get if we have preemptive scheduling, in which case you don't control anything. So between any atomic instruction, it can get interrupted and then the other thread could execute. So you can see how this can get out of control quite fast because you would have to argue about any single interleaving between the instructions, right? While instead, if we had cooperative multitasking and essentially, we just had these instructions, which is our plus plus count, and then after them you just had a yield. So you wouldn't run into this scenario if you just did all those instructions and then only yielded your CPU after you did those 3 operations or the whole plus plus count. You wouldn't have any data races. Yeah.
But then we're not doing anything like concurrently, right? Like that's what we're getting at.
So it would be concurrent, right? Because it could do this thread, switch to the next one, it could add 1, then it could add it again, and then it could switch back to the other thread, could add a few more times.
But like those 3 commands would not be like concurrent, they would happen one after another.
Yes. Yeah, because remember with cooperative multitasking, you have to yield out the CPU. So if you want to make sure you do those 3 operations before yielding, and the only way to take away the CPU is by you yielding it, then you can avoid the data races and things like that. But you would still get concurrency because as soon as you yield, it could switch to another thread. Yep.
Yeah, I'm not sure about how it's concurrent after yielding. Like, so basically we're processing the 3 statements, right? So once you've done those 3 statements and then we yield, so isn't that the same as like just completing one completely and then switching over to the next task, which is not the same as concurrency?
Yeah, so for this to really illustrate concurrency, those 3 operations would be in a loop, right? And both threads would be executing them like, in our example, like 10,000 times. So you could switch between what thread does it. But it's not really concurrency if it's only just incrementing once and then dying.
Oh, so basically any other thread could take it and that's basically concurrency.
Yeah, so you can pause it, do some work on another one, pause, go back and forth.
Makes sense.
Yep.
If there is only like one CPU and you kind of have to do these kind of things, what like actually is the benefit of threading? Because it seems like it's not like speeding up the calculation. If you can't do it in parallel, you're not really speeding up the calculation. So like,
Yeah, so the question is, if I just have a single CPU anyway, what's the benefit of threading? It's doing the same amount of work, but it's just context switching all the time. But sometimes it's actually easier to write threaded programs if you want to do multiple things at once. And instead of like, okay, I'll do this, save my state and like restore it later and go on, you just use a threading library and it's all done for you. So you also might, field multiple requests, do multiple things at once, and it just makes the programming much, much simpler. And also, even if they're kernel threads too, instead of user threads, then you could also have a thread do some I/O operation that gets blocked, and then the kernel can run another thread. So it can actually kind of interleave work because you're waiting for hardware or something like that. Well, if you had a bunch of user threads, then you're screwed anyways, right? Because you'd be blocked. And yeah, that whole user threads versus kernel threads, very good thing to know for the quiz. So yeah, to analyze data races in general, you have to assume all preemption possibilities. So what I'd kind of, whoops, I didn't switch. So to analyze data races, you have to assume all the preemption possibilities. So I called the reads R and then like the number to see what thread they were from. So there was read 1 and R1 that always have to happen in that order, and then read 2 and write 2 always have to happen in that order because they're within the same thread. So we'll assume no reordering in threads. Your compiler can actually do a bunch of weird things, but it wouldn't do it in this case anyways. So these are all the possible orderings. So if you start with a read 1, the next operation you could do is either a write 1 or a read 2, and then as soon as you have and then after the write 1, you'd have to read 2, or you could write 2, but at that point it doesn't matter. In that case, the count would be 2. But if we do our 2 reads at the beginning, it doesn't matter what order our writes are in, we're just going to get 1 as the answer after those 2 threads run. And then this is the execution where thread 2 just completes first and then thread 1 goes, in which case we would get count correct again. And then this is the case where the second thread reads first and then the first thread reads, and in which case you're just going to overwrite the same value with 1 again, and the count's going to be off. So if you assume like equal probability of it getting interrupted between any instructions, the odds are not in your favor that you're going to get the result that you expect. Okay, so this is introduction to mutexes, which won't be on the quiz, but is what will be the next topic and what you'll need to know for lab 3. So essentially, to prevent data races, you can use something called a mutex. If you want to answer questions about the quiz, we should have plenty of time. We can kind of blast through this. So you can create mutexes statically or dynamically. So statically is just kind of like a global variable, and dynamically is on the heap, of course. So init would be on the heap, or you can do this to essentially initialize it as a global variable. And then if you want to include attributes, you have to use a dynamic version. We'll just see how to use a mutex. Yeah.
When you're doing it dynamically, are you using like malloc to give it space, or?
Yeah, so pthread init would call malloc for you, pthread mutex init would call malloc for you, and then you have to destroy it. So it's a bit of a different API than what you're used to. So this init will, under the hood, call free for you, and then you have to call destroy on it, and it will call free for you. So yeah.
Sorry, so I know you said that global variables are not stored in the stack and they're not in the heap. What is the name that like preloaded piece of memory called?
You can call it just global space if you want. It has a bunch of weird technical names that don't make any sense. You can just, global variable for now, or just global space, or it just lives within the process. Okay, so that's creating a lock. How you use a lock is, it's kind of like a real life lock. You can lock it and unlock it. So by default, when you create it, it's going to be in like an unlock state. So you'd have some code, and then you'd call pthread mutex lock, and after that point, no other thread can make it past the pthread lock call. So this code is protected, so if multiple threads came and made it to this lock call, what lock guarantees is that only one makes it past that call. So you don't have any data races because there's only going to be one thread in that protected code at a single time. So only one thread will be between the lock and unlock. So as soon as you call pthread unlock, that means, hey, this thread is done with the lock. Another thread can go ahead and enter that protected code, right? So everything between lock and unlock is protected. Only one thread can be between that, or only one thread can be running that protected code at a single time, right? And a topic we'll see in a later course is deadlocks, which are essentially you can brick your program, and that's another complication of having to deal with all this threading stuff. But there's also, so lock will also just kind of sit there and block or wait until you can acquire the lock. If you don't want to do that, there's a function called try lock that will just try the lock and say whether you got it or not, but we don't need to know that for now. So if I go back to my example, yep.
So essentially, like in between the two lock and unlock, it just makes that section like an atomic instruction, essentially.
So it's not an atomic instruction. Just only one thread can be executing that at a time. So other threads can't execute that. But, you know, it wouldn't be atomic because if, hey, another thread was doing the same thing and didn't acquire a lock, you would have the same problems as before.
Right.
Yeah.
So is it kind of like when this statement is in the run function, when we're creating the threads, whichever thread reaches it first, it kind of like gets the access and the others just wait for it to finish.
Yep.
The protected code.
Yeah, until it hits unlock. Yeah, so if we go back to our example before our count, so we could fix the data races by doing something like this. We could declare a mutex that just lives as long as the process lives, and then we can protect our ++ counter because we know that contains our data race. So we could have a lock here and then a unlock here, and that way we would have the same result every single time. So we can go ahead and see that too. So here it is. It's the exact same code, except I have a lock and an unlock. And now if I execute that, right, I get 80,000 like we'd expect every single time, right? So now we don't have a data race. But what we did is essentially now it's kind of like single threaded, because if that's our only operation we care about, and between the lock and unlock, there's only one thread there at a time, essentially only one thread will ever execute at once, and we don't have any parallelism whatsoever, right? Yep.
Is there overhead added with the lock?
Yeah, so the question is if there's overhead associated with that, and yes, there is. Yep.
In the example, it was saying like M1, so I assume you can have multiple muxes,
Mutexes.
And if so, what does that allow you to do?
Yeah, so the question is, I assume you can have multiple mutexes, what does that do? And we'll see that later. Because multiple mutexes gets really, really, well, not really, really, but it gets kind of bad.
Is anyone coding GIMP? Or
Jimple?
sorry.
No, it's just like a compiler representation. Okay, so if we go back to our demo, what this does is now, tablet. So now if we back up, oh God. So now this was kind of an example of our data race, right? But now if we have locks and unlocks, the first thing that thread 1 would do was call lock here. And now if it context switches to here, the first instruction that the other thread would execute is lock. And because thread 1 now has that lock or that mutex, then this wouldn't return. It would just essentially wait a while and then yield the CPU. So this instruction would never be executed because it wouldn't get past the lock, right? So it would just sit there, wait and wait and wait, and then eventually it would context switch back over to thread 1, and then execute then execute the increment, and then even after the increment, if it tried to switch back, right, it would hit the lock and just sit there again, and it's still waiting for the lock. So it wouldn't do anything if it got preempted after that point, and then it would write out the memory location and then call unlock. Yep.
Wait, so if we supposedly have, like in the previous example with the compute 80,000, supposedly have like code after the unlock,
Yeah.
would the second process, will it still be stuck before the lock and not run the stuff after the unlock?
Yeah, so the question is, if there was some code after the unlock, could the other thread just kind of do that while it's waiting for the lock? And the answer is no. Within a thread, it's going to run sequentially, right? So it hits the lock, and it's going to wait until it can actually get the lock.
During that time, it just does nothing and it's just eating up CPU.
Yeah, it depends on your lock implementation. So it could eat CPU time, it could be put to sleep, it could be whatever your lock implementation is. Yep.
So lock is one atomic instruction then, because you can't. What if thread
Yeah.
is midway locking and then thread 2?
Yeah, so lock is, you can think of lock as, it's atomic.
And what if like these two threads are in parallel, let's say, and they both hit lock at the same time?
Yeah, so if the threads are in parallel and both hit lock, it's atomic, and smart people that made your CPU will make sure only one of them actually gets the lock. Yeah, because generally your lock will be represented by like some memory location, so there's going to have to be some ordering even if they execute that in parallel. Yep.
So we define protected code as like no other thread can touch it.
Yeah, so any protected code will only have one thread executing it at a time. And that way we don't have data races because we're not fighting with any other threads for that protected code, or the more general name that you'll see is it's called a critical section. Yeah.
So essentially with locks, we're basically undoing our whole purpose of multi-threading, right? So
Yeah.
why are we doing that?
Yeah, so the purpose of lock kind of sounds like it undoes the purpose of multi-threading, but you're going to need to get locks to get the correct answer sometimes, right? If you have a data race, you're just going to get inconsistent results, and if you get the wrong result faster, is that actually better? Yeah, right? So you still need to get the correct result, and locks help you get the correct result. So there is a way that you can just make everything in parallel and just let it kind of go, but you'll get the wrong result. But you'll get it fast, but it won't be right. Right, like would you want the code without locks to calculate your grade for the course? It only gets lower. Remember, our count was 80,000 when we ran it a few times. It was just randomly way lower.
8,000% is high.
No, it
Could
could
still be
higher.
higher.
It's 80,000 out of 80,000.
Start at 100 and just gradually peak decrements your grade based on what you failed.
Yeah, yeah. Sorry?
If you like don't initialize count,
Oh, I initialize count.
you'll get like over 100% your grade.
Yeah, if I don't initialize count, your grade will be like some really high number. Maybe, that's like rolling the dice. Okay, all right. So that's adding a lock to prevent data races. We'll see that again later. So the code between the lock and unlock, again, is called a critical section, and that, again, only means one thread executes that at a single time. So it guarantees safety, aka mutual exclusion, which just means one at a time. So there's only one thread in a critical section at once, and this is what you need to do to actually like implement locks. The other property is called liveness. So if multiple threads reach the critical section, in which case they're trying to call lock, then in order for your lock to actually be useful, one of them and only one of them has to proceed through that call. If none of them proceed past that call, you won't have a data race, but then your program won't work, so that's not very good. And the critical section shouldn't depend on outside threads. You can mess up really easily and cause a deadlock where threads don't make progress, and we'll see that in the next lecture. We don't have to worry about deadlocks today. And then the other property you must have is something called a bounded wait. So if a thread makes it to a lock call while another thread has the lock, you want eventually the waiting thread must eventually proceed, otherwise your program might get stuck. And other properties you want to have when you program it and make critical sections. So that was a good point about, hey, aren't we just making our program slower? So the goal when you are writing programs like this is you want to make the critical sections as small as possible, because essentially anything in the critical section can't be run in parallel, which is going to be very, very slow. So you want them to have as little overhead as possible or just wasted time. So you don't want to consume resources while waiting too. If you're just sitting at a lock call and using 100% of the CPU, you're not doing any useful work and you want to avoid that. Also, you kind of want your locks to also be fair. So each thread should kind of wait approximately the same amount of time. You shouldn't favor one thread over the other. So you can hopefully get more of an even distribution of what thread is actually doing what work. And of course, like with anything in programming, all your interfaces and locks should be easy to use and hard to misuse, which is easier said than done. So similar to libraries, whenever you make applications that use multiple threads, you'll want different layers of synchronization. So like the comment about, hey, shouldn't that pthread mutex lock be atomic? Well, yes, it would be atomic, but you can imagine that by itself, any implementation we kind of can think of to create a mutex probably has issues. So you need some hardware provided atomic operations in order to implement the locks. And next slide, we'll see our attempt at creating a lock. And then above that, you'd want some high-level synchronization primitives like mutexes that are much easier to use. And then building on those, you hopefully have your properly synchronized application. Yep.
What happens when you just never call unlock? Do you just end up with like a bunch of zombie threads or something?
Yeah, so the question is, what happens if you just never call unlock? So if you never call unlock for this, so if I just like delete this line, yeah, so if I never call unlock, then it will never so a lot of bad things are going to happen. So if I never call unlock, any other thread would never be able to get the lock because it's unlocked. So even if I have two threads, they both make it to the lock call at the same time, and then thread 1 gets the lock, and then thread 2 is going to wait there. And then if thread 1 never calls unlock, thread 2 is just going to wait there forever. So, and then it's not going to finish, right? And also, if you lock a lock that's already locked, that is undefined behavior, depending on the lock. Yeah.
So let's say thread 1 has a lock first and then unlocks. Thread 1 will eventually go back
Yeah.
to the lock.
Yeah.
Does it stop or?
Yeah, so in this case, because it's in a loop, thread 1 could, lock, unlock, and then it could still be running, so it would just get the lock again, do the operation, unlock again. So you don't know how many times it goes and gets the same lock again and again, right? And then it would context switch over, and then thread 2 might get the lock. But it could get the lock multiple times in a row.
Right, I mean like if you just never call unlock, right? And then
Oh, if I never call unlock?
and then thread 1 hits the lock, but it has control over itself.
So if it locks an already locked mutex, that's undefined behavior, and it will do something bad. Okay, so let's see what we could do to implement a lock. So to implement a lock, if we have just a unit processor system with just, one single core on it, then our only source of concurrency is interrupts. So if we want to lock something, we just disable concurrency, and you can disable concurrency by disabling interrupts. So this is what our implementation could look like if we just have a single core and our only source of concurrency is interrupts. You just disable interrupts and that's your lock, because now you can't get interrupted after that lock call, and then your unlock would just be to enable interrupts, right? Yep.
So user code can disable the kernel from stopping it?
Yeah, so that's a good point. So the question was, so user code can disable the kernel from stopping it? And the answer is no. So this would be like the implementation in the kernel. So this isn't a valid implementation if you're implementing locks yourself, because of course, the operating system or the kernel will not let you change hardware and will not let you do that. So as a lowly user process, you're not allowed to do that. So it's not going to work on multiprocessor systems, and it's not going to work for user processes either. So this would only work if you yourself are implementing locks in the kernel, and you could make a system call so users could access this if you really want, but this is the only way of doing that. Yep.
So why does a uniprocessor allow this, but a multiprocessor doesn't?
So on a uniprocessor, right, if you only have one core and your only source of concurrency are interrupts, if you disable interrupts, you won't have any concurrency anymore. So you don't have any issues, right? Yep. Okay. So let's try and implement a lock ourselves. So if we try and implement, say we're trying to implement a lock ourselves in software, so we have an init function and we have a lock, and then say, we just assume that the user allocates for us an integer, we're going to represent our lock as an integer. So initially, we're going to have the value of our lock as 0 to say that it's unlocked, and we'll use the value of 1 to say that it's locked. So our lock function could look something like this. This sounds reasonable. So the while loop would just execute infinitely while that lock is 0. So basically, while it's locked already, it's just going to wait over and over again until it sees that the lock is unlocked, right? Because the only way to pass this while loop is if the lock value is 0. Everyone on the same page for that? Okay, so if it makes it out of this while loop, it would then write the value 1 to indicate that this lock is now locked. And then that would be our lock, and then hopefully no other thread could call lock and get the lock, right? Because it would go through this while loop, and now the lock value is 1, so it would just infinitely go through this loop. It would waste a bunch of time. And then in our unlock, all we do is we set the lock to 0. So anyone wants to tell me what the issue is here? Yep.
A data race
And what's an example of the data race?
Like let's say you just unlocked it, and then another thread was just about to run set the thing to 1.
Okay.
So it just locks it again, and now you'll never get out of it.
So let's see. So let's just argue the lock. So the lock function kind of looks like while that lock value is equal to 1, we spin infinitely, and then we set the lock equal to 1. Do that. And then initially, let's just assume that the lock is unlocked, so it's equal to 0. So what could happen, so say we have thread 1 and thread 2, and we'll assume we're just on a single core, so only one operation can happen. So so what's an example of our data race? You want thread 1 to execute essentially this read, right? Or sorry, this, right? So this is our read operation. So if, say, thread 1 executes first, it's going to do the read. And what value is it going to read? 0, right? I said initially it's 0. So I'll say initially it's unlocked. So it would read L equal to 0, right? Which would mean that thread 1 would, equal 0. So 0 does not equal 1, so it would break out of the loop, and then the next thing that thread 1 would want to run is this instruction right here, right? It would want to write out 1 and change whatever that lock is, or that it would want to change that integer value to a 1. Well, it's sitting there waiting, and because this is a preemptible thread, we'll assume preemptible ones, it could context switch over to thread 2. So now thread 2 would execute, and it would come in and execute this read. So if it does this read, what value is it going to read? 0, right? And then now at this point, both thread 1 and thread 2 are at the same point, which is right here. And now they're both going to write the value. Now it doesn't matter what executes. They're going to write L equals 1 or L equals 1 here. And then both threads are going to make it past the lock call, right? So 2 threads call lock, and then 2 threads return from lock, and now they'd both be executing the critical section at the same time, which means our lock implementation is completely invalid, right? So this was our attempt at making a lock. It seemed like a good idea at the time, but we can see threading is actually kind of hard, and it doesn't work, right? Any questions about this? Yep.
What if you put the star L equals 1 before the while?
Before the while?
Yeah.
Like
Then you'll be stuck in the lock.
like
Forever.
here?
Yeah.
Equals 1? Yeah, so then the first one that comes in is they'd both try and write 1, and then they'd both read 1, and then neither is going to return from lock now.
So that's a deadlock.
Yeah, which is kind of like a deadlock, although if the lock worked properly, it should have worked. But yeah, so either we have a situation where both threads can make it by, which is not good, or neither thread can make it by, which is also not good. We want exactly 1 to make it by. Okay, so that's, in this case, this implementation is not safe since both threads can actually be in the critical section at once. So this is not a valid lock implementation. And it's also not efficient because we have that while loop that just keeps on reading memory over and over again. So so in the next lectures, we'll actually see what that's like. So any questions about anything or related to quiz 1? Are we good? Yeah.
You said you're going to be posting the quiz content on the outside?
Yeah, I'll post like the content stuff on what we don't need to know. Yep.
Would you say the best way to study for the quiz is just reading the lecture slides?
Yeah, so a good way to study for the quiz is just kind of going over the lecture notes. I'm not going to put any questions on there that we haven't covered or at least talked about. So like anything involving processes or all the fun stuff we did. Any of the programming stuff we did, you don't need to know, but like any conceptual things are valid.
What about our labs, like lab 1, right? We just did it, so like.
Yeah, you don't need to know anything about lab 1. Lab 1 is supposed to be review, C review, which apparently is really funny, but there's no C review. There's like hash table questions. I don't know what it would be on.
Our last C course was like first year.
2 years ago,
Yeah.
that was covered.
Yeah, well, don't worry about the quiz. Pulling for you. We're all in this together. Also, Thursday if there's like a big panic, we can do review on Thursday or we'll see. Okay.
Thank you so much.
Yeah. Also, I have office hours now if anyone wants to follow me back. I'll be in my office till like 4:20.